In this module, we look at how particles in a system are distributed over states with different energy and introduce the Boltzmann distribution. A fundamental idea of quantum mechanics is that the energy of a particle, a molecule, atom, or electron confined to a region of space is quantized, meaning it can only take specific discrete values. These allowed values of energy are called energy levels. The smaller the mass of a particle and the smaller the region of space it is confined to, the more widely spaced its energy levels are. Quantization of energy is crucial for describing electrons in atoms and molecules. For macroscopic objects, the energy levels are so closely spaced that energy appears continuous and quantization can be safely neglected. Let us now consider a system or ensemble consisting of a large number of indistinguishable particles, such as molecules or atoms in a macroscopic sample of a chemical substance. Each particle can have energy equal to one of the energy levels, that is, one of the allowed values. In statistical terms, when the energy of a particle corresponds to a specific energy level, we say that the particle occupies this level. Each particle in the ensemble can also be in different states, which is a broader concept than energy levels. In this context, we also say that a particle occupies a state. Multiple states can correspond to the same energy. All particles in such states, meaning all particles that occupy states with the same energy, are said to occupy the same energy level. Due to continuous interactions between the particles, their states and energies are constantly changing. While we cannot track individual particles, we can describe the average number of particles occupying each state and energy level. In statistical terms, we say that particles are distributed across different states and energy levels. This distribution is described by the population of states in the ensemble. The population of a state is the average number of particles that occupy it. Regardless of the nature or type of states in an ensemble, their populations are always governed by the same formula. This is a formula derived by Ludwig Boltzmann and known as the Boltzmann Distribution. It relates the populations of two states, I and G, denoted Ni and Ng, and says that the ratio of their populations, Ni divided by Ng, is equal to the exponential of minus the energy difference between the two states, epsilon I minus epsilon j, divided by Kb times T. Here, Kb is Boltzmann constant and T is the absolute temperature. Remarkably, for a system with a given set of energy levels, this distribution depends on only one parameter, the temperature T. Instead of comparing the populations of states, we can also interpret the Boltzmann distribution in terms of probability. The probability that a particle in a system at temperature T is found in a particular state I with energy epsilon I is proportional to the exponential of minus epsilon I divided by Kb times T. In this simple introduction, we will not discuss the normalization of this probability. The population of a state and the probability of being in that state are directly related. In fact, for a large ensemble of particles, the population is just the probability multiplied by the total number of particles. The Boltzmann distribution gives us several important insights into how particles are distributed over the available states in a system. First, two states having the same energy are equally populated and equally likely to occur. Second, if state 1 has a higher energy than state 2, then state 1 is less populated than state 2. The higher the energy, the less likely it is that the state is occupied. Now let us consider the effect of temperature, which is illustrated in this figure. At absolute zero, all particles occupy the lowest energy state, the ground state, and all higher states are completely unoccupied. As the temperature increases, higher energy states gradually become more populated, and the distribution spreads out. At very high temperatures, as temperature approaches infinity, all states become equally populated. In physical chemistry, it is common to express energies on a per mole basis. To do this, we define the molar energy of a state, which we write as capital EMI. It is equal to Avogadro constant times the microscopic energy epsilon I. With this substitution, the Boltzmann distribution becomes the probability that a particle in a system at temperature T has molar energy EMI is proportional to the exponential of minus EMI divided by R times T, where R is the universal gas constant.